All right, hey everybody. The this lesson we're going to be looking at getting, drawing vectors, what they represent, and then we're going to look at scale diagrams for adding, subtracting vectors, and even calculating things like average velocity. Right, so it's going to be scale diagrams for now. A little bit of the math introduction for it as well, but not for angles cases. So we're going to have lessons where we can deal with vectors at angles nicely. We'll do it by scale diagrams and by mathematical methods as well. So here we go. Here's a question that's along the lines of something you saw in the previous lesson, just as to get started here. So if you're walking along from school, this is that walk from school question, right? So it might have looked something like this. In which case, if you look at the distance you've traveled, then it'd be the 50 plus the 50 plus the 150 and so on, right? So this would literally just be the total of all the numbers. That would be your distance traveled. And then your displacement would be the straight line distance from where you started to where you ended up, right? So your displacement would be that purple arrow. And so if you're looking at that as far as a size goes here, you might be able to intuitively look at this and say like, well, we got 50 is that size. This is just drawn roughly, right? But relative to one another, I think it's decent-ish. So if you put a bunch of 50s together, you might be like, okay, well, we got 100, 200, 240, something, whatever, right? You might say about 240 or so for that. Just based on what it looks like, right? Based on those green arrows and approximating and so on. The other thing we can do is we can say, okay, well, if this number here, actually, what was it? It was 50. We got 100 there, 150, 350, 400, 490, looks like it is. So that ends up being 490. And so obviously we can calculate some things, right? Our speed would be the distance over the time. So I can just write in here distance over the time. And so your speed, your average speed overall would be your total distance, that 490, if I got that right, divided by the time was 3 minutes. And so we're looking at 490 divided by the 3, giving us, about 163 meters per minute. I'm not worried about whether or not this is realistic or not. It's just meters, so I don't know. Maybe more than 3 minutes might have been good, but I'm not sure how many. It's hard to picture, right? How many meters per minute you can walk. Maybe they're riding a bike or something too. So who cares really? But yeah, so we have that as our number, and so we're probably going to approximate this as about 160 meters per minute or something, right? One thing that we talked about in the last lesson is if you're looking at your average velocity, right, then it's your displacement over your time. And so in which case we're only talking about 240 as a total divided by the 3. So the 240 divided by 3 gives you a nice easy number really, but 8 times 3 is 24, right? So gives you 80 meters per minute, right? Because it's just what you ended up as your effective overall velocity. You could have just went straight. The idea is you could have just went straight from home to there if you like bushwhack through or take a straight path or whatever. At 80 meters per minute, you'd end up at the same spot in the same amount of time. Okay, so that's the idea of that from what we've seen so far. We are going to come back to this one and look at how we could add this up mathematically, since we have all nice 90 degrees, no angles to deal with. Okay, so we'll come back to that, and that'll lead us into get us used to the idea of adding up the numbers mathematically as well once we're ready to do that for angle cases. So with vectors, you can represent things with vectors, obviously. So this vector here of the A vector it is here, whatever number that might be, it's at 60 degrees. And so for the directions of things, we have ways that we can communicate the directions, all right? And so in this one here, this one's my preference, this direction would be like east 60 degrees towards the north. That's what that means, okay? So you're starting from east, you're facing east or whatever, and then turning 60 degrees towards the north. I find that one just most intuitive, right? That would be the same as, obviously equivalent to if you face north and turn 30 degrees towards the east, right? So those are equivalent. So again, same deal here, right? Your starting direction, turning whichever way. Okay, so it doesn't matter which one you're using as your reference point to start from. That would clearly define that red arrow direction. Another way to describe this would be this one is 60 degrees north of east. Right, that's a way you might see in a book somewhere, or textbook, or a teacher might use that method or something. It might be their preference, but certainly it still describes things. Right, you're 60 degrees north of east, or 30 degrees east of north. Okay, that could be another way. And then in the military and in programming language and that, they often use bearings. And so this a bearing is when you start from north and you rotate clockwise. Okay, so the A vector there would be a bearing of 30 degrees. And they like it in military, I think, because it's like simple, like less to say, right? A bearing of 30 degrees, there's less chance for confusion or needing to be told the format of it. You can always just say the same sort of thing, you know. I find it not as intuitive though, obviously, right? Like bearing of 30 degrees, you have to know you're starting from north, things like that. And with the green vector, you know, saying like south 10 degrees west is pretty quick and easy to visualize, right? Face south, move 10 degrees towards the west, or face west and turn 80 degrees, right? Or you could say 80 degrees south of west and stuff like that, right? So those should make sense. The bearing for this one would be, you know, the full 180 degrees plus another 10. So it's a bearing of 190 degrees. But picture that, right? To me, I find that a little weird to say, because, you know, you're like, okay, face north and then turn 190 degrees to face the way the direction is meaning. But those are just common ways to communicate directions of vectors. So using that, then we can draw scale diagrams of things. So if you had a scale diagram where you're letting 1 centimeter represent 1 meter, or it could have been meters per second, so 1 centimeter would represent 1 meter per second, or, you know, whatever, right? You can represent any vector quantity with arrows. And so if you're drawing this, you'd want to draw a 6 centimeter long arrow that is south 25 degrees east. So facing south 25 degrees towards east. So it's going to be that kind of direction right there, following my mouse pointer, right? So facing south and then rotating 25 degrees towards the east. Okay, so that's the vector delta D, the displacement vector. Okay, so that's a delta D vector there. Wouldn't hurt to have that be red to go along with the vector, I suppose, right? So that, you know, that represents the vector. If it was a velocity vector, then it would be representing, you know, a velocity vector of 6 meters per second. So it's 25 degrees east, right? So the vector, it's a vector, of course, as a review, because we've got the size and the angle, right? So it's a vector because we've got the size and we've got the direction. Okay, so just again, scale diagrams can represent any kind of vector. In this case, we're looking at displacement and velocity. There's going to be lots more as well. There's going to be force, there's going to be lots of things later on. So the next step is to look at the idea of adding vectors. And so right now we're just looking at the idea of it. We'll come back and actually do it with this, even mathematically. But the idea is pretty clear here in this one as well, right? Where you walk this way, then you walk that way, and so on. If you looked at these as a bunch of displacement vectors, you'd have a displacement vector like that, and then one like that, and then one like this, and so on. And so pretty naturally, what we're seeing here is we're putting these things, what we call tip to tail, just line them all up and to add them up, right? And so the process is called placing them tip to tail. So we have the tail and the tip of a vector, just like an arrow, right? And so we just literally just add them up. This is a bunch of displacements, one after the other, and so they're combining one after the other and adding up, right? And so what that would look like, something to recognize here, is that 6 plus 3 plus 2 in this context would not equal 11, right? And that's because angles matter, right? And so if you're drawing this and trying this and so on, you'd literally just be, drawing arrows like this, and just copy and paste each one on here to work with it a little bit live here. But tip to tail, you're just walking this way and then that way and then that way and so on, and then your displacement ends up being from where you started to where you finished. It's pretty obvious stuff, right? So the idea is exactly that. Okay, so if we did this as a scale diagram, say this was 2 centimeters and that's 3 centimeters and so on. I don't have it. Let me just do this here. Let's copy this. But you would literally just measure and make them the right sizes, right? So if I measured this thing and had it be, that was supposed to be 2, right? So I'm going to change the scale to be, so my ruler, I would have just said, okay, 2 centimeters is representing my 2 meters and so on. Let's have that. And I'd have this one lined up as being 3, and then this one lined up as being, or measured out to be the 5 or the 6, I guess it is, right? So looking at it there's your 6. And then quite literally from a scale diagram, then you could just measure this thing and say, okay, we've got 5 point something, right? So 5.3 meters from the measurement of the 5.3 centimeters, okay? Your scales don't always have to be 1-to-1. I'll try to make sure to do an example where you might have something like 1 centimeter equals 2 meters because you need to shrink the thing down, in which case you have to be able to work with the scale and determine answers. Okay. But as you can see, of course, the idea of if you put them end to end, it would be 11 meters, whereas the actual displacement vector is, of course, a lot shorter. Angles matter. Okay, don't get looped into that mistake. So this applet doesn't work anymore, but I can just show you the results of it. So this is showing like a vector of like 26 and 15. As you stretched out the just clicked and made the arrows, it would show you what the lengths were. And then it shows the result of the addition of the two of them, right? And so again, 26 and 15 doesn't give you 30, 41 or whatever, right? It gives you 25 because the angles matter. So this one's a little older. So it just doesn't work anymore. I want to show actually. So this is the first one where we can actually do math for it because we have enough skills from previous math classes. We can do that. So I'll just move this one to this page and make room for it. But obviously it's saying like, it's showing 20 plus 30 gives 36. Well, you could measure by a scale diagram, of course, and make it happen. Or you could actually use the Pythagorean theorem because the math is simple enough. I don't have to teach you anything new for this, right? So again, this ruler version of things here, copy, paste onto there. So let's set up a scale here. We could even actually just use the grid, I suppose, that's there. So see how they have it drawn. Let's do that easier. Although I'll change my mind here, because the diagonal is going to be hard to measure up, right? And so let's set up a scale and use it. So this is supposed to be 20. So let me get rid of this stuff. We'll do that one later if needed as well. Or I'll show it to you at least. There you go. All right, so let's set up a scale here that's a little harder to work with and to show you how to do it. So if we had my ruler set up, just how it worked out, if you decided to use a certain scale or whatever, I'm going to set this up so we have 3 centimeters is the 20. Okay, so here we go. Almost 3. That's close enough probably for what we're going to do, right? So my scale I'm going to set up here is, and I'll use, is 3 centimeters on my diagram. So I have basically a scale here where it's diagram to the application or whatever we're trying to solve, right? And so I have 3 centimeters and it represents 20. Okay, and let's just see if the applet agrees with what I've done here. So what should this length be if the applet is correct? Hopefully it is. If not, I'll have to abandon ship on this. But let's just go for it here. So basically it should be representing 30, right? And so basically what length should represent 30? So I'm just going to show you how easy it is to work with ratios, to work with things like this. So basically we want to see like, what is this answer, right?
Well, all you have to do is figure out what the multiplication is to go from this one to this one, like on the top, 20 to the 3, in order to see what multiplication would work to give you the number here, and then you just do that multiplication and make work, right? And so all you have to do is always think of this as your like first number and your second number, the one you're starting at, that you want to start at, right, in order to go the direction you want to go. So my first number is my 20 and my second number is my 3. Well, what multiplication factor is that? It's not easy to tell. If we were going from something like 2 over to 10, it'd be easy to be like, oh, it was times 5, right? Well, that comes from the 10 divided by the 2, right? So it's your second number divided by your first number always. Okay, so I'm doing this as a pretty obscure ratio to show that the power of being able to work with ratios makes it so that it doesn't matter if it's easy numbers or not. Okay, so I'm trying to give you the skills needed to be able to deal with any situation. So your multiplication factor is a 3 divided by a 20. So if I multiply by 3 over 20, then I'll end up getting my number, right? So we need to do the 30 times the 3 over 20. So I'm going to do 3 over 20. My multiplication factor is 0.15. Multiply that onto the 30, and it says, okay, it should be 4.5. Okay, this should be 4.5 centimeters. And that's just the multiplication of the 30 times the, right? Let's do this. 30 times the 3 over 20, where this comes from, would be the 4.5 using the scale. So now let's just do a quick check to see if my diagram is to scale, and so we can trust the answer if it is, right? So this should be about 4.5. You look and be like, yeah, okay, I see it's matching pretty good, right? So there's your 4.5. So we can trust our results within that sort of level of it working well. And then we have, just one sec here. All right, I'm back. Here we go. So that's the 4.5. That's the number it should be, right? So then we can take this ruler and match it up and see what length it says in centimeters. And then our job is then to convert to the application answer, right? So basically it's like, I don't know, let's say 5.7 centimeters. Okay, so the result, R, the A plus B equals R, right? So A plus B equals this R vector, right? Well, from the diagram, the scale diagram, was, what did it say is 5.7, was it? 5. Let's go 5.6 or 7, 5.7. So 5.7 centimeters, right? And so then you convert to the answer, right? What would that be then? So the result or whatever, the answer, based on the application, it represents speed or whatever, right? We need to figure that out as well. So let's use our ratio. So we're going to have our ratio. I always recommend just to start with your ratio as you know it. So diagram to the application, we know is a 3 to 20 ratio. And then we have our 5.7 centimeter result. And so in this case, we need to figure out what this one is, right? And so that's when we do, from the start to finish, we need to be able to go this way this time, right? And so my first to my second here, my second divided by my first this time is a 20 divided by 3. So we're multiplying by a 20 divided by 3. So we get our 5.7 times the 20 divided by 3. So let's do that. 5.7 times the 20 and then divide by a 3. It gives us a 38. Okay, so I'm getting an approximation from my scale diagram of 38. Well, the beauty of this question is that we can use math to figure this out as well. So that's good. That's from a scale diagram method. But the mathematical result we can actually do, since we know the Pythagorean theorem. Oops, should be a capital for Mr. Pythagoras. So we have, let's just do a screenshot of that
triangle to make it easy to describe here. And so obviously we have a right triangle. Pythagorean theorem is just sum of the squares, sides add up to the sum of the square of the big side, right? And so we have what for our numbers? It was 20 and what was it? 20 and 30. 20 and 30. And then we're wondering what this should be. And so we have a 20 squared plus a 30 squared equals an r squared. So we can just do the numbers. So we're going to have the 20 squared is the 400. Oops, blue here. Second. We have the 20 squared and the 30 squared. So we have our 400. Trying to find my black pen here. The 400 plus the 900 equals the r squared. And so then we can just add those up and take the square root, right? So plus, add those together, you get 1300 r squared. You can just do the root of both sides. And it's going to solve for r. And we're hoping it's going to be fairly close to this answer of 38. So root of 1300. Here, I'll do this on calculator here so you can see what I'm doing. I think this one I have to type it in first, 1300, and then boom, the square root of it. So the actual mathematical answer is 36. My 38 approximation was pretty good, right? So 36 is our answer, the actual result. So if I did a bigger diagram and was more careful with measurements and so on, I'd get closer and closer to 36 with more and more accuracy. All right, so decent result there, I'd say. And all of the different types you can do that with. This one here, because it's at angles, it's a little trickier, obviously, mathematically, right? So you could use sine or cosine law, I suppose, if you're really on top of that mathematically. But there's going to be a way that we're going to use in class that's even easier than that. So we'll get to that when we get to that. It's a couple lessons from now because I have to teach you about components of vectors first. So adding vectors, it's just another applet, basically showing, if you could do a lot of practice with this questions that are here, because you could do a scale diagram of 30 at 60 degree, north 60 degrees east, and draw a vector that represents 30, and so on and so on, and see that you're able, see if you're able to get the answer of 36 and a half, okay, to confirm how to do things. This program that you can click on here, that link works still. It's in a really nice graphing program called GeoGebra, and it's set up. It's a program that someone set up in it, and you can make any two vectors you want and add them up, and it'll give you the results. So then you could check to see if you can match it as well. It says the result right there is like a 121.66. If you add 80 at an angle of 0 and so on. I included this one so that you can make lots of practice questions and see how close you can get from your scale diagrams, but also because it shows a method there. So this right here, if you move this vector over, really is that tip to tail idea of like adding this vector to that vector. But they show it like this because a lot of people just like it. It's the parallelogram. I don't even know why people like it that much, but the diagonal of a parallelogram, if you set up 2 copies of each of the vectors, you make a parallelogram. The diagonal is the addition of them. I don't know why people like that so much. It's so non-intuitive, really. What's much more intuitive is the idea of like adding up the vectors tip to tail, because you're walking this way and then you're walking this way, and so you went this way, right? Putting another copy of the vector here and another copy of the vector there and making a parallelogram and finding the diagonal doesn't add any understanding value to me at all. But I showed it to you, so there you go. Hang on a sec here. All right, sorry about that. I had a sneeze come in and I didn't want to sneeze right into the microphone. Here we go. So if we're looking at subtracting vectors, okay, one method that works is adding the opposite. So you're thinking of adding or subtracting A and B. Where do I want to go here?
So basically, we already know how to add vectors, and so it kind of makes sense. You could think of like 7 take away 3 is the same as 7 adding negative 3 to it, right? Just algebraically. And so if you wanted to do A take away B, then you can think of it as A add negative B. So you just have to think of what that negative B vector looks like and literally just add them up, right? So you could make a diagram where you're adding the negative vector and so on. You could make a scale diagram, you could measure and so on. Okay, so nothing new there other than just saying, okay, we add the opposite instead. So I'm not doing an example, but obviously you could do a scale diagram and make that happen. I want to focus more on a way nicer method, in my opinion, where you're going to put them tail to tail. Okay, so it's called tail to tail subtraction. And I want to show you why this makes sense and how nice and easy it is. So if you wanted to, again, do A take away B, you could place them tail to tail, just like that. And you think of this one as your initial position and this one as your final position, right? Obviously, your change in position is always the subtraction, like your final position minus your initial position. So that's why it makes sense, all right? So your direction analysis of this would be you'd go from your initial to your final position. The only thing I didn't like about tail to tail was I had trouble remembering which way it goes. But really now, if you label it as initial and final position, clearly the direction is this, right? From initial to final, okay? So if you just draw the vectors tail to tail, which is super easy, you just make this, draw this one, tail to tail, then label them as your final minus your initial. Any subtraction is always, think of it as final minus initial. So whatever it happens to be, Q minus W, then your W is your initial, so W to Q would be your direction. Yeah, so you can just draw that diagram and measure. As long as you've drawn this to be the scale length and you've measured the angle of it and so on, then it just gives you the value, right? You can just get the value from a scale diagram for now, and then we'll do math versions of it as well. Okay. So directions of things, let's do a practice of this. If we're doing X minus P, we'll put them tail to tail, right? And then P minus X would also be the exact same diagram, tail to tail. We just have to think of it as final minus initial, right? So if this is final minus initial, then you could label on here, okay, well, that's my initial and that's my final. This subtraction would be this way. This is the X minus P vector. Whereas in this case, your final minus your initial, your X is your initial, and this is your final. And so in this one, that's your vector. So this is the P minus X vector. So it's actually really easy to figure out the direction. You just have to remind yourself that any subtraction can be written as a final minus an initial. Okay, so that's your tail to tail subtraction method. But at that point, you just draw the vectors, right? So you would have, established your angle system and so on, and put this at the right angle here, and made this the right length, and put this at the right angle, and made this the right length. Then you just measure, right? Just measure the result. So, and the angle too, by the way, right? So you can measure the result. I don't know if I did that or said that before, but you can measure the angle of the result. You can measure the length of the result, all that stuff, right? So back up here, when I did scale diagram of this, we get that length, but we also could measure the angle, or in this case, because it's a nice right triangle, you could even do math to get the angle, right? So this angle here, right? Angle meaning direction, right? We could actually just measure it. Or in this case, we could do some math for it, right? So the math would have been to say that angle would be, we'd have the 30 and the 20. And so you could say, okay, well, tan, because you have your opposite and your adjacent, right? So just reviewing some math for you as we go, because we need it. Tan of theta equals opposite over adjacent. And so you'd do tan inverse of both sides and get the angle, right? So tan inverse to get rid of it gives you the number. So in this case, the angle would be an inverse of the 20 over the 30. So 20 divided by 30 and we do tan inverse. So in this calculator, I have to hit that little button there, do tan inverse. So it should be about 33.7 degrees or so, right? So 33.7 degrees. And if you measured that, I don't know if I can do this on the fly quick here or not. Let me just see if I have a protractor. There is protractor. Around here, there's a protractor. Oh, that'll work, right? So you can put that in place and see what kind of angle we are at. A little hard to read, but that should be 33.7. Here we are at 10, 20, 30, 33.7. You can tell it worked pretty good. All right. Here, so subtracting vectors, we can do all that stuff too. Obviously, this then, if you started at 6 meters east and ended up at 9 meters north, 20 degrees west, you can just draw the diagram, right? It's nice to, if you draw rough sketches of the arrows first. So if you're measuring and getting a scale, you'd be like, okay, we have one that's like 6 meters east, one that's 9, so longer than that, and north 20 degrees west. So north 20 degrees west. You think, okay, I've got these 2 arrows. I need to be able to put them tail to tail. Obviously, I'm going to have to, move my stuff down here, right? So you can make things work out. But if you've drawn this into scale so that this represents your 6 meters east, and this represents your 9 meters, and it was at 20 degrees, right? There's your 20 degrees. You measure to the protractor and so on. So you're going to need to get a protractor for this stuff. So stop by your local store or wherever you want to go shopping. But yeah, you need a protractor to do this. Maybe a math teacher in the school might lend you one. Yeah, so remember, this is the issue. The thing I do have to remember to tell you about this question is we want to find the displacement. Okay, so displacement is your final position minus your initial position. So like that. And so we ended up at 9. So this is my D2, my final D2, D2 and D1, or final initial, mean the same thing. So this is the final position. This is the initial position. When you're drawing this thing, this absolutely right from there to there, when you measure it and so on, this would be your displacement. Okay, so that's allowing us to calculate things. That's when I said here at the beginning, where I said here, we're going to be determining displacements. That's how we're doing it so far with scale diagrams. Okay. Yeah, so there's the work that's all carried out basically, and so on, the ideas of it. So see if you can draw a diagram that works out the same as that. And then the last part is to say, okay, well, and then from that we could actually calculate velocity, right? So if it took 2 seconds for that to happen, you'd have your number from the diagram, and then you'd have it divides and gives you the velocity, the average velocity. Okay. I want to point out that dividing a vector by a scalar is defined in math textbooks as a process that works. You get a vector result. That's defined as a vector property. In physics, we just think of it as common sense, right? That we're dividing the displacement by the time, so or we get a velocity that's going to be in the same direction as the displacement, of course, because that's what we calculated. We understand the meaning of what we're doing, and so we don't have to think of it as abstract definitions. It just common sense, makes sense. So these ones are subtraction examples. So in that same link, you can just click on subtraction, and it'll do subtraction versions. So you can generate as many as you want, as easily anytime you want, and practice to make sure it works. If you're getting answers. Then the only other thing I want to show quick here is the idea of how we could do this with math. So basically the trick is first to establish a reference system. So if we establish a reference system like this, thinking, okay, that's my X and that's my Y, and this is my positive X and positive Y and so on. How it works is you add up all the X's and Y's. We're going to call those components later on, but I don't have to right now because they're literally just the vectors, right? So basically we have a 50 over and we have a 50 up, and then we have a 150 over still. Think of this as your journey where you're going, this way and then you're going this way, and then you're going this way, and then you're going this way, right? And so on. And so when we get to the spots where we went down, that's going to be a minus 200, isn't it? Right? So that's going to go in as a minus 200 because it was down, and then a minus 50, and then a minus 60, and a minus 30. Just do a double check to make sure I have that all. 50 up, 50 over, 150 over, 200 down, 50 left, 60 down, 30 left. Yeah. So those are all my directions. And so then you can actually just add up all those results and it'll give you the overall result. Okay, so that gives us, when you look at the overall result in the x direction and y direction, we have that result. And so we have 100, and then we have 150, take away the 30, 120, I guess. And then we have negative 260, so negative 210. Just literally just add them up, right? So if I showed you here the 50 minus the 200, move this so we can see it, minus the 60, you're just adding them up, okay? And so it gives us a total displacement. Oh boy, that's all grouped, isn't it? So you get that result. And then you need to do, so I need to ungroup that so I can organize this. All right. So you do need a little bit of math to get these results. And so from that, basically we have this triangle, right? This is the triangle here, but I'll just redraw it so that it's easy to see. That, right? And so these are our results. We have, it's 120 over and 210 down, right? You could put the minus on if you want. It just means down, or means south in this case, right? Or in the negative y direction. So this result here for displacement we can get mathematically because now we've converted this thing into a right triangle, right? So this is going to be the root of the sum of the squares. Just use the Pythagorean theorem directly or go right to the answer like I'm doing, right? Plus the 210 squared. If you want to throw the minus in, it doesn't matter because it gets squared out. So we're going to have 120 squared. Where's my square button in this calculator? I'm not seeing it. Why am I not seeing it? Power of my x to the y button. What the heck? Because I'm in inverse mode? Oh, that's why. Okay, so my x squared, so 120 squared is 1440. So root of 14,400. And the 210 squared is 44,100. 100. And so I have to add those up. So 14,400 added to that gives me a total of that. And then I just need to do the square root of that, giving me 241. And we had approximated earlier 241.86, we had approximated earlier that it was around 240, just based on the idea of the logic we're talking about. Okay, so that's pretty sweet, right? You can see that works nicely. You've got a magnitude of this 241.87. And the other benefit as well now, is you look and you can say, oh man, we can actually even get the direction of this thing, right? Because the direction would be right here. Let's do that in purple, I guess. So this direction right there, use theta for direction like we do in math often, right? You can say, okay, well, tan of theta equals opposite over adjacent. So we got the 210 over the 120. You don't want to include the negative there because that can introduce weird mathematical artifacts or whatever. You just want to get that angle. So the 120 opposite over adjacent. And then we just need to do tan inverse of that. So 210 divided by 120, and then tan inverse. So 60.25 or so degrees, so 60.3 degrees, let's just say. So, right, all I did is do tan inverse of both sides. And that works. So now we have the displacement vector, right? Displacement equals 241.87, whatever, maybe say 89, 241.9 maybe, just rounding to reasonable numbers. And we can even say that it's, east 60.3 degrees south. Okay, which again is something you could measure from your diagram as well. So if I went back to my protractor onto here and flip the protractor around to be able to measure that angle, how do I want to hold it here? Put it in here like this, and we have, 10, 20, 30, 40, 50, 60, it's a rough diagram, so it's not actually drawn to scale, but it's pretty cool that it's working out as good as it is. I was just approximating. I was saying like 50-50, and then I did 3 of them, and then I did 4 of them, and then I did, a little, these ones are estimated a little more, but you can see that's working pretty nicely as well. All right, so the math process of keeping track of the X and Y parts gives you the total X and Y, which is very logical, and it works amazing. And that's going to be the root of what we're going to be doing once we figure out how to work with the angles versions of things. So notice that this would be harder to do in these cases because you don't have, you can't. This isn't just an X or a Y, and so that's what we have to tackle next. Being able to deal with when they're not just X's or Y's. Right, so that is it for scale diagrams and some mathematical introduction work for working with vectors and when you're adding or subtracting them. Right. So as always, if you have any questions, let me know. And until next time, thanks for watching.